Good morning and welcome. I think we can start this morning session. So my name is Jennifer Xu. I'm an assistant professor at National Tsinghua University. So I'm from here. So today, this morning, we have talks to give us an overview about the two of the largest collider experiments at LHC, the ATLAS and CMS. So first of all, let's welcome my colleague at Academia Sinica, Dr. Wang. He'll give us an overview talk about the recent results in Higgs and the exotic atlases. So let's welcome Dr. Wang.
Good morning, everyone. So first, I'd like to thank the organizer of this workshop for inviting me to this talk. So as Jennifer mentioned just now, so I'll talk about the recent results in the Higgs and the exotic searches at the ATLAS experiment. Okay, so here's a very simple outline of my talk. I'll start with a brief introduction to the LHC, the ATLAS experiment, and then I'll briefly review the results on the measurements of the standard model Higgs boson and the searches in some of the exotic topics, and then conclude the summary. So as you know, at the LHC, there are four main experiments. So we have the CMS, the ATLAS, and then the LHCb and the ALICE experiments. So the LHC is a proton collider, but it also can collide heavy ion particles. So during round one, the machine operates at a center of mass energy of 7 and 8 TeV. And in run 2, which is occurring right now, the center of mass energy increased to 13 TeV. And here is a picture of the ATLAS experiment. So starting from the central part of the detector, we have the tracking detector, which allows us to measure the charged particles, to identify the primary vertex, and also to identify the B jets. And then surrounding the tracking detector, we have the electromagnetic and the hadronic calorimeter, where we use that to construct So, as I said, surrounding the tracking detector, we have the electromagnetic and hadronic calorimeter, where we use it to construct jets and also to identify electrons and photons in the electromagnetic calorimeter. The outermost detector is our muon spectrometer, where we can identify the minimal ionizing particle that escape the detector. And then we have two magnet systems. The solenoid that surround the inner tracking detector provides a magnetic field around 2 Tesla. And then the toroid surrounds the muon spectrometer, provides a magnetic field of 1 and 0.5 Tesla. Okay, so some words about the LHC and ATLAS upgrade. So just like I mentioned about the round 1 data taking, so at that time we were colliding with the protons at 7 to 8 TeV. And then both the machine and the experiments undergone the upgrades between 2013 and 2014. And after the upgrade, the machines provide us an instantaneous luminosity for the run 2, which can increase up to 1.6 times 10 to the 34, and we expect to collect an integrated luminosity between 100 to 150 inverse petabond for the run 2 data taking. And after the run 2 data taking, we will have what we call the phase 1 upgrade, where the instantaneous luminosity will then increase to 3 times 10 to the 34, and we expect to have an integrated luminosity of about 300 inverse petabond. So the run 3 will last between 2021 to 2023. Then after that, the machine and the experiment will go through another upgrade, where we'll go into what we call the high luminosity LHC run, where during this time the instantaneous luminosity will increase to 7 times 10 to the 34, with an average about 200 interactions per bunch crossing. And during this time, we will expect around 3,000 inverse petabond of collected data. Okay, then some word about ATLAS during the run 2. So here's a table of the numbers for round 1 comparing to run 2. So during round 1, the peak instantaneous luminosity is around 0.8 times 10 to the 34, and the experiment collected about 25 inverse petabond. So for run 2, the instantaneous luminosity now has reached to 1.4 times 10 to the 34, and we have collected around 36 inverse petabond. The average pileup is around 24 interactions per bunch crossing, but if you look at the distribution here, you can see that in some cases the tail can go up to around 40 to 50 interactions per bunch crossing. Now, comparing between run 1 and run 2, you can see that for most of the standard model process, the cross-section increased by a factor of 2 to 4. But if you are interested to search for heavy particles, you will be quite excited because the cross-section can be quite large. It increased, in some cases, increased by a factor of 40 to 50. And if you are interested in the quantum black hole, the cross-section can increase by a factor of 700 or several hundreds. So run 2 allowed us to increase the search sensitivity for very heavy particles. Okay. So as I mentioned just now, in 2013 and 2014, the experiment went through upgrades. So during this time, Atlas has included a fourth silicon pixel layer, and this greatly increased our tracking performance. So shown here is a plot of the B-tagging efficiency. So for example, comparing between run 1 and run 2. So for example, if you detect the B jets at 70%, you can see that the rejection factor for light flavor jets increased by more than a factor of 4. So this really improved our analysis in terms of detecting B jets and rejecting the background. And then for the trigger side, the level 1 trigger data taking rate has increased from 75 kilohertz to around 100 kilohertz, and the HLP output rates increased from several hundred hertz to 1 kilohertz. So we have a bigger bandwidth to collect more data. And the performance for identifying electrons and muons also stayed at very high efficiency. So the electron efficiency ranges between 80 to 95% depending on what is the purity of the electrons that you want to select. And the muon ID efficiency is also staying very high within the muon fiducial volume. Okay. So at the LHC, we would like to answer the fundamental questions to particle physics, and models which are created to address these questions and make predictions allowed to provide guidance for us to conduct such search. And we make use of the unique features predicted by these models to guide us to perform the searches. And we also make use of benchmark models to interpret the results that we find in our data. So listed on the left here are some of the guiding models, and on the right are some of the signatures predicted by these models here. In some cases, a single model can make several predictions of different signatures, and in other cases, a single signature can be predicted by several models. So if we were to conduct a search in one single model, we are able to probe several models at the same time. So in this case, we would like to perform our search in as broad and as general as possible. Okay, so for this presentation, I'll mainly present results that are primarily from the iChat 2016 conference. So I apologize to the audience if you already know the results. And so the results I'll be presenting will cover some of the standard model measurements, and then I'll talk about searches for new particles, mainly in the resonance search in the dilepton, diphoton, dijet, and diboson final state. Okay, so let's start with the standard model Higgs boson. Okay, so as you know, in round 1, we have discovered a standard model like Higgs boson with a mass around 125 GeV. So for round 2, we would like to re-establish this again by searching the Higgs boson in this production channel with the gluon-gluon fusion, the vector boson fusion, the Higgs production in association with the W and Z boson, and then Higgs production in association with TT bar. So shown here is a table of the predicted cross-section for a Higgs mass of 125 GeV for this different production process. So the process of gluon-gluon fusion gives you the highest production rates. And this table shows the decay branching ratio for the Higgs boson at 125 GeV. So the largest decay branching ratio is in the BB bar final states at around 58%. And you can see as you go down the table, the branching ratio decreases. In the case of a muon paired decay, the branching ratio is really small. Okay, so we start with the Higgs to ZZ to 4 lepton final states. So for this analysis, we categorize the search events into different production channels. So as you can see, we divide our selected events into gluon-gluon fusion, the associated production, and the BBF production. And this plot here shows the 4 lepton invariant mass distribution of the selected events, and you can clearly see an excess here at around 125 GeV. And in the mass range between 118 to 129 GeV, we observed 44 events with an expected 9.7 background and 22 signal events. So using this measured data, we measure a cross-section of 81 picobarn compared to standard model prediction of 55 picobarn. And these measurements allow us to make this plot where we show the kappa F versus kappa V, where the kappa F is the coupling strength to fermions, and the kappa V is the coupling strength to vector boson. So in the case of standard model, these two measurements should be at around 1, but instead we measure for kappa F is around 1 and kappa V is slightly higher. This is because we observe more events in the BBF and enriched channel, but it is still within the standard model. Next is the Higgs to diphoton. So for this analysis, we perform several measurements. So we measure the prediction cross-section and the differential cross-section. And we also categorize the production in different channels. So shown here is the diphoton invariant mass for the BBF enhanced channel. And you can also clearly see there's a bump at around 125 GeV. The top right plot here shows the differential cross-section measurement as a function of the diphoton PT distribution. So the black point here is our measurement, and the blue band here shows the predicted cross-section from the Wang fusion channel. And the dashed green histogram here shows the cross-section from the other production channel. So the traditional cross-section measurement that we have the cross-section times branching ratio we measured is 42 femtobarn compared to the standard model of 62.8 femtobarn. So we are slightly lower, but within the error. And the bottom right table here shows what we call the signal strength, which is defined as the measured cross-section divided by the standard model cross-section. And you can see the signal strength for various production cross-section, various production process. We have the TTH, DH, VDF, and Wang fusion. So all the measured signal strength all clustered around 1. So the combined signal strength is 0.85 plus minus 0.21. Okay, so this plot here shows the measured cross-section at different central mass energy. So from round 1, we have two measurements at 7 TeV and 8 TeV. And then for 13 TeV, we have another set measurement. The green point is for Higgs to ZZ, and the red is for Higgs to gamma gamma. So the black point is the combine of the two measurements. So for 13 TeV, we have a local access, local significance at 10 sigma. So we rediscovered the Higgs boson in run 2. Then next measurement is the Higgs to BB in the W and Z associated production. So for this measurement, we perform in 3 different leptonic channels. For the 0 and 2 lepton channels, we probe the Higgs production in the associated production of ZH, where Z decay to 2 neutrino for the 0 lepton, or Z decay to 2 leptons in the 2 lepton channel. For the 1 lepton channel, we probe the WH production with W decay to a lepton and a neutrino. So for this measurement, the dye B mass distribution is very important as a discriminating variable. So we perform corrections to improve the mass resolution. So as you can see, the original distribution is this black histogram. And after applying the correction, we are able to improve the resolution by 15%. And the right plot here shows the MBD mass distribution in the 0 lepton channel, where the main background comes from the Z plus jet production, followed by W plus jet and TT bar production. And the expected signal contribution is shown in red here. So the bottom table shows again the signal strength measurement for these 3 different channels. And the combined signal strength is 0.21 plus minus 0.51. So this corresponds to an observed significance of 0.42 sigma with expected significance of 1.9. And this can be compared to the round 1 sensitivity, where our observed sensitivity is 1.4 sigma and with the expected sensitivity of 2.6. Now the next measurement is the Higgs production in the BBF channel with Higgs going to BB bar, and followed by a photon that's coming from the initial state radiation or photon coming from the W exchange. So for this case, this extra photon allows us to have an extra handle on the trigger, and furthermore it helps to suppress the multi-jet background. Then for this analysis, we make use of the vector boson fusion production properties to allow us to discriminate the signal from the background. So for example, we make use of the delta eta distribution between the two forward jets. As you can see for the signal, the two forward jets are much more separated compared to the background. And then we know that in the BBF production, the two forward jets are quad jets compared to the multi-jets per background where we have a mixture of gluon and quark. So we look at the jet width distribution as our poor man kind of quark and gluon separator. So using these properties, we try to separate the signal from the background, and we search for the signal in the NBDS distribution. So we have two categories, the low sensitivity category and the high sensitivity category. And here is the expected signal times a factor of 10. So with this, we are able to set a limit on the cross-section at 4 times the standard model. Next is the TTH production with H to BD. So with this measurement allow us to measure the top Yukawa coupling, and the search is done in events where one or both of the W decay electronically, and we categorize the search according to the jet multiplicity and the number of B jets. So in this selection, there are 4 B jets in the final state, so one needs to find the proper BB bar pair from the Higgs decay. So shown here is the Higgs mass distribution. For the open histogram, this is the predicted Higgs mass from the signal, whereas the red histogram is the signal where once you find the right BB bar pair for the Higgs signal. Okay. So the bottom right shows the signal strength for the dielectron channel and the single electron channel, and the combined signal strength is 2 plus minus 1, which we have reached the same sensitivity compared to round 1, where you have 1.5 plus minus 1. Okay. Now there are also other new standard model Higgs search results which I have no time to present. So we have Higgs to 2 muons, TTH where the H decays into a multi-electron final states. And we also have the VVF or the WH production with Higgs to 2W. So I'm sorry I have no time to go through all this. So now I come to the beyond standard model searches. Okay, so in this case we try to search for new resonance, and if we were to find some excess in the distribution, of course that would be very nice. Otherwise we set a limit for some benchmark process. So I start out with searching for resonance in the lepton transmitting ET final states. So in many beyond standard model, it predicts new spin-1 gauge boson particles where they are heavy version of the standard model WZ bosons. So for this analysis, we search for the W prime that decays to an electron or muon, and the neutrino. And the benchmark model that we use is this sequential standard model. So here are the two transverse mass distribution that we search for the resonance. So the left plot is for the electron channel, and the right plot is for the muon channel. And the black points here are the observation from our data where we do not see an excess above the expected background. And the green, blue, and red histogram, these are the predicted signal coming from the W prime of different masses here. So by combining the electron and muon channel, we are able to exclude the W prime mass below 4.7 TeV in this sequential standard model here. And if we compare to round 1, we can see that our excluded mass has improved against the round 1 by about 1.5 TeV. So here is an event display of the event with the highest transverse mass, and in this case it's in the muon channel. So here the muon has a transverse momentum of 2 TeV, with a missing energy of 1 TeV and the reconstructed transverse mass of 2.9 TeV. So next is the search of the resonance in the dilepton channel. So for the left plot here shows the search in the dilepton channel of opposite sign. So here's a distribution in the dimuon final states. Again, we do not see any excess in the distribution. So when we combine the electron and muon channel, we set a limit on the Z prime mass to 4 TeV, and you can compare to the round 1 measurements which exclude mass below 2.9 TeV. So again, we improve the sensitivity by more than 1 TeV. And then on the right is the search in the dilepton, where you have two same sign, and in this case is in the EE final state. So again, we do not see any excess. So we use this result and interpret in the left-right symmetry model, where we set a limit on the doubly charged Higgs. So you have the left-handed and the right-handed and left-handed, where we set the mass limit on them. And in this case, we assume that the doubly charged Higgs decay to EE, to a pair of electrons at 100% branching ratio.
Sorry, I'm confused about the inequality. Should that be greater than?
Which one?
Oh,
so this is excluding the mass below.
Oh,
Okay. So here is the event display of the events with the highest dielectron mass. So in this case, the both electron is close to 900 GeV, the transverse energy, and the reconstructed mass is 2.38 TeV. So you can see the two electrons very nicely balanced against each other. All right, so now I'll move to searching in the dijet final state. So in the QCD, we predict a smooth falling spectrum, and here we try to search for a bump. So the left is for including a dijet search, and you can see we probe the dijet mass all the way up to around 7 TeV, and unfortunately we still do not see any access. So we set limits on several benchmark models. So for example, like the excited quark, we exclude mass below 5.6 TeV, or the W prime mass below 2.9 TeV. On the right side, we have the exclusive search, where we require at least one of the jet to be a B jet, which allow us to probe the excited B quark production, where the B star decay to a gluon and the B quark, or Z prime decay to a BB bar pair. So again, we don't see any excess, so we are able to exclude excited B mass below 2.3 TeV. Okay, so here's the event display of the highest dijet mass event. So here are the two jets at around 3 TeV, and the reconstructed dijet mass is 7.5 TeV. So you can, again, in this Lego plot, you can see two very nice jets with very little activities around. Okay, so now I come to diboson searches. So here we are probing many production process, and one can also look at many different decay channels. So for example, in the BD production, you can have 4 lepton final states, or 2 lepton plus missing ET, 2 leptons plus 2 jets, and so on and so forth. So you can see there's quite rich final states to explore. And furthermore, we can also perform the search in a wide range of the boson transverse momentum. So in the case of low transverse momentum, the boson that decays hadronically, the 2 jets will form the 2 small cone jets. However, if this boson would be highly boosted, then the hadronic decay of the jets will be reconstructed as a large cone jet. So this diboson production is predicted in many new physics models. So if we were to observe an excess in one of the channels, then we are able to measure the relative strength in the coupled channels. So for example, like comparing Z gamma production to diphoton production. And for the di-Higgs production, we are able to use it to constrain the Higgs self-coupling. So I start off with the the high resonance in the BB final state. But first I make a slight detour to round 1. So in round 1 we observe a slight excess in the QQQQ final stage, where at around 2 TeV we observe about a local significance of 3.4 sigma. However, we do not see any significant excess in the other 2 channels, the L-QQ and the LLQQ final states. So in round 2, we want to check again whether do we still see this excess. So here is the round 2 result. Again, we perform in these various final states. We have the LLQQ, and we also have a new channel, the UNIQQ, the LUQQ, and then followed by the all hadronic final states. So in all these channels, we do not see any excess. For the QQQQ final states, we do see a small excess at around the same mass, but in this case, it's only 1.9 sigma. So it's not as significant as in round 1. Okay, so the results that I showed earlier, we then interpret in the W prime model and also in the RS graviton model. So here is a plot of the upper limit cross section for the W prime as a function of the W prime mass, and you can see the results from these 4 different decay channels. So for the LUQQ, you see that it has the best sensitivity at the low mass region, whereas at the high mass region, the LUQQ, the all hadronic, and the UNIQQ, they have more or less the same sensitivity. Okay, next is the resonance in the VH channel. So here the Higgs decay to BB bar and the Z and W bosons we also explore in the various decay channels. For the analysis, some of the analysis focus only on the boosted region where we search for mass above 1 TeV, and other analysis combine both the resolve and the boosted channel, and they expand the search from a range of 200 TeV to 2 TeV. So here are the search results. The top 2 are the search in the new BB and the LBB channel in the resolved channels, and the bottom is the LBB and the QQBB in the boosted channels. So in these 2 plots here, the open dash histograms are the predicted W prime signal at a mass of 2 TeV. And using this, we set limit on several models. So for the top left here, we search for a CP odd Higgs boson decays to a ZH, where you can see here is the cross-section limit that we set for a mass range from 200 GeV to 2 TeV. And the top right is the cross-section limit for Z prime mass from around 1 TeV to 5 TeV. And the W prime limit shown on the bottom left here, you can see we set a limit between 1 to 3 TeV. At around 3 TeV, we see an excess around 3.5 sigma, and at 1.6 TeV, there's around 2.6 sigma. So there are some slight excess here. We don't want to get excited yet. We would like to cross-check again using the rest of the 2016 data set. Okay, now I come to diphotons. So I guess you guys know a lot already on the 750 GeV access, but I still need to go through this. So here is the event display of the highest diphoton invariant mass events that we had in 2016. Here you can see 2 nice energetic photons, each of them with a transverse energy around 1 TeV, and the reconstructed mass at 2.2 TeV. So as you know, in 2015, we observed an excess of 3.9 sigma at mass 750 GeV. However, after reprocessing the 2015 data, this excess dropped to around 3.4 sigma, and the peak shifted to 730 GeV. And this is because after reprocessing, one of the events get migrated from mass of 757 GeV down to 722, and then one event was removed due to the isolation cut on the photon. So, and on the right plot here shows the 2016 data where we do not see a significant excess. So combining 2015 and 2016, now the excess dropped to 2.3 sigma, and the peak is around 710 GeV with a width at around 10%. Okay, now I move to die-Higgs production. So in standard model, it predicts the non-resonant Higgs pair production of through this square diagram or this triangle diagram. And for the beyond standard model, it also predicts Higgs pair production. In the non-resonant case, the production may be enhanced by modifying the Higgs coupling constant. Or one can also have resonance production with heavy particles that decay to two light standard model like Higgs boson. So in Atlas, we search for the Higgs pair production in various decay channel. So I'll start off with the BD gamma gamma final states, where one of the Higgs decay to a pair of B quarks and the other